Century. That's by the Tragically Hip. Ah, here it is. Good, good, good. All right, here we go. First thing we climb a tree, and maybe then we talk, or sit silently and listen to our thoughts, illusions of someday, cast in a golden light, no dress rehearsal. This is our life. And that's where the hornet stung me, and I had a feverish dream with revenge and doubt. Tonight we smoke them out. You are ahead by a century. You are ahead by a century. You are ahead by a century. Stare in the morning shroud, and then the day began. I tilted your cloud, you tilted my hand. Rain falls in real time, and rain fell through the night. No dress rehearsal, this is our life. Well, that's when the hornet stung me, and I had a serious dream with revenge and doubt. Tonight we smoke them out. You are ahead by a century. 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 And disappointing you is getting me down. Hydrate or drive? Absolutely. That is good. Dihydrogen oxide. That is very, very good. Dihydrogen oxide.
Okay, that means it's time to start, huh? All right. Hey. Good evening, everyone. Do we have? All right. I guess I have some audio there. Good enough. Good evening. This is Double Tribble's channel on Twitch, streaming live on August 11th, I think, August 11th, 2024. My name is Ron. I live in rural New Hampshire, surrounded by forests and animals and all kinds of stuff. And I stream technology and science and movies and a whole bunch of other stuff. So, I did the last science. Last night we did a movie night, and then before that, I think it was Thursday or Friday, we did a science stream, and we were doing black body radiation, and we I did an experiment, a couple live experiments. One of them wasn't much of an experiment, but at least one real experiment, and where we went through this whole thing about black body radiation and how electricity goes through a conductor and heats it up and can heat it up to the point where it emits radiation in the visible spectrum. That's what you call an incandescent lamp, right? Incandescent light. And there are a bunch of things on that. We had a bunch of questions about it. We went through some formulas, and we talked about Planck's constant. They couldn't explain, when they were first learning all this stuff, finding out about it, scientists, they couldn't explain, how that function went when the temperature went up, what kind of energies at what wavelengths happened when temperature went up. They couldn't explain it. And they had all kinds of ways to try to explain it, and they couldn't explain it until Planck came up with this idea of putting in another constant, Planck's constant, into his formula, his equation, and it worked. And that led to a whole bunch of other things. And we were talking about things, and we were looking at the some of those graphs, of how the temperature how the frequency is affected by the temperature, and it's if you have a light at a certain frequency, each photon has a certain amount of energy, and that amount of energy in an individual photon goes up proportionally using Planck's constant. So I had questions about I had a when it goes way up, we watched the video, and the guy said if it goes way up, then it turns blue, right? Because there's a whole spectrum. On one end of the spectrum, right, is red, and the other side is blue. But these graphs have a particular shape to them. Let me see if I can bring this up here. I'm all set up for another experiment here. That we're going to do another black body experiment that might be. It won't be as dramatic as the one we did the other night. The other night there was fire and flame and smoke, and it was pretty dramatic. You can look at the VODs to find that. But there's a. I'm going to go ahead and bring up a browser window here, if I can, and we'll look at these things, and I'll talk about it a little bit. Here we go. Okay. All right. So this is temperature. It's not quite what I wanted, but we can get there from here. All right. I don't understand. Wikipedia, for some reason, keeps changing their interface, and it's kind of There it is. Okay. All right. So, so I'll type in black body. That'll get it. Black body radiation. There we go. Okay. All right. So they got these curves here. You know. And I was trying to understand how you could get blue light. I can understand how you can get red because, you know, as this wave, you know, this wave starts, you know, for things that are like ordinary objects and stuff, it's way down here somewhere, right? It's, you know, just radio waves or whatever. Everything emits black body radiation, by the way. Radiation, thermal radiation. Everything. Everything in the universe, because you can't get down to absolute zero. They have experiments where they can kind of do it using resonance and lasers and stuff like that, but you know, everything in the universe emits radio waves. And but as the temperature of the thing, of anything, goes up, once it gets to a certain point, then this part of the scale of the thing starts to creep into the visible range here of wavelengths. And so I can understand that, okay, it gets up here and then it gets into the infrared, you know, far infrared, near infrared, and then this end of the thing starts to creep into the visible range, and then, okay, you can get red only, you know, and then you can get orange and then yellow. But then as you start going further and further here, it starts including all of these colors. Could you see how this graph? Can you see that? Yeah, you can see my point there. It starts including all of the colors, and if you include all the colors of rainbow, it's white. That's, you mix all the colors and you get white. If you mix them all equally, and if you mix just this, you know, like right here, this would be mostly red. It's infrared, and then red, and then this isn't going to hardly show up at all, but it's going to be mostly red. And as it creeps this way, then it gets yellow, a brighter yellow, white, almost a white. Here, same thing. And then this would be pretty much white, right? This one here, they got it colored blue, but I think that would be white. So I'm thinking, how can you get, if once you get past here, then everything's going to be white. It's just going to get brighter and brighter, right? More energy. But if you think, as it gets further past this point, then you start looking at this end of this slope, which is much more gradual. The front end of it is steep. The back end is more gradual. See that? And there was let me see if I can find another. There was another a GIF. I think I'm going to have to go to the Creative Commons website. Let's see here. Hang on just a second. We'll get this. Body visible spectrum GIF. That's the one I think it is. There we go. So this is right here is a GIF. It's kind of complicated and it moves kind of fast, but what we're looking at here is this thing as if you were changing the temperature of something. And as the temperature goes up, so here's a lower, here's 300, 3,000, 4,000, 5,000. As the temperature goes up, this peak shifts, gets further and further, or higher frequency, shorter wavelength. And you go from, if you're just looking at the visible spectrum here, it goes from looking at this kind of slope, then this kind of slope, and then this kind of slope, and then if you keep going up, then it'll be this kind of slope. See, like this on this side of it. So that's what this little GIF here shows. Oh, great! It's not very big. Sorry about that. Is there a zoom in here? I don't know if I can zoom GIFs. Yeah, we can do a little bit. All right. So you see what we're looking at here? This is the red, and blue, violet, 400 nanometers, 700 nanometers, NMC nanometers. And so what this GIF is showing you is taking something and what it would look like from a relatively low temperature of, what is it, 1000 K, and then increasing it to a high temperature of 25,000 Kelvin. K is Kelvin. Or 30 maybe. I don't know. I can't. They're going so fast. I can't tell what they're getting up to there. I wish there was a way to display this, slow it down. But you can see what it's doing here. See how steep it is there, but then when it gets to the higher one, you're looking at the back end of this curve. See, this more gradual curve and steeper on this side. So what happens? And I thought, well, if you keep increasing, it's just going to be white. But when you get way up there, when you get up to this point here, way up there, then there is more blue than the other colors. It's still white, but blue is mixed in, and you can see the color here, the actual color that it comes out as. And it's kind of a pale blue, blue when it gets way up there. See? So it is possible to get blue. I thought it wasn't. The guy said it was, and he said a star. One of the stars, Spike, I think it was. That's about 18,000 Kelvin. And so there's a way to get there. And also I said something about, well, you can't get temperatures on Earth that are that high, and of course we can. In experiments in labs and stuff like that, we get really high temperatures. So they can get high temperatures. I looked at arc welding. Arc welding makes ultraviolet, and they have to wear special visors and all that stuff when they're arc welding to filter out the UV. And so I was, looking at that and trying to understand what those temperatures were. But those are just like on the low end of this scale, actually, right? They're maybe a couple Kelvin or something like that. They get white, but they don't get really blue. Okay. And so you can get blue. It's a pale blue. it's kind of a lot of white with a little blue mixed in, and a whole bunch of UV. A lot of on the beyond the visible spectrum. So that I just wanted to clarify and explain some things that I said that weren't right. There were a few other things that I said that weren't right. I mean, it's just a live stream. I'm going to say a whole bunch of things that aren't right, right? So I want to clear up the ones that I could remember that I said that were not correct. All right, so let me bring back my mug. So we corrected some things, and then we'll get into some more stuff, an experiment. I'm going to do an experiment. I found a camera. I was trying to use an old camcorder to look at this as we burned up a piece of copper wire. I wanted to see if we could see it glow in the infrared before it did it, but it went too fast, and the camera wasn't sensitive enough. But I found a camera, an old camera that has a special filter and stuff on it that it'll take pictures in the near infrared. You have to light, if you're just taking pictures of something, it won't take like those infrared pictures where the temperature, whatever temperature somebody is, it glows up. That isn't what it does. It still requires an illumination with a infrared light source to take pictures of something, but it'll work for this experiment that I want to do. So I got that set up. We'll do that. But before we do that, I wanted to I had a whole bunch of followers. We got Sandra Henry 01 who just followed me. Thank you, Sandra. For some reason, my alerts don't work. My follow alerts. I went through everything on this. I'm learning. I'm not even a month into this, and so I'm trying to learn this stuff. I thought I had it set up so my followers would give an alert, as I'm streaming. It would at least put a little message up or something that says that somebody follows me, but it doesn't do that. I don't know why. Eventually I'll learn. But I got a bunch of followers that I never thanked on stream. So I'd like to go through some of those here. Sandra just followed me just now. Thank you, Sandra. Ms. Jellybeans followed me. K Pars. Teo. Zach App gave me a really nice raid, my very first raid a couple of days ago. Thank you, Zach App, and he followed me, so that's cool. Zeo Duck. Pete the Feet 1. Reeducator, I think. Mushroom Back something. Erebro. I have trouble pronouncing the names. Some of them make sense visually if you read them, but they don't make sense if you try to pronounce them. So, thank you all for following me. We had also Textures Plunky, Bounce House, 42, AW Board, Unknown User. That's a cool one. Chan follow up Chan the Magic Man. If you want to watch Chan, he does it as a magic stream every Monday evening. He does a magic stream. Peekaboo Draws followed me. The Roach Official. Big Ducky Snow, Steven. He's a loyal watcher of the stream so far. Sloth Lounge. Swiss R. I was speaking with Swiss R in chat and got a follow. And Happy Nightmares followed me. Thank you. Sydney Akakoko, I think. Thank you. Misty Kitten. And I got a shout out from Chan at some point there that I don't remember. That was a long time ago. But anyway, I just wanted to go through that because my alerts aren't happening, and I'm not able to thank people contemporaneously, except for Sandra Henry, which I just did because she just followed me a few seconds ago. So that one I could do contemporaneously. All right. So I wanted to make sure I get that, and I'll try to figure out how to get those alerts working. Maybe I'll watch some YouTube videos or something. Maybe somebody will say, "Oh yeah, you forgot to do XYZ" or whatever, So the other thing was Planck's equation. Yeah, that was the other thing. We wanted to. I was all confused about the difference between the relationship between Planck's constant and the amount of energy in a photon and the frequency, which has a linear relationship, and then Planck's law, which is exponential, and explains that curve. Remember, I was telling you how they couldn't understand. They couldn't understand how this worked. Here's the theory, right? This is the theory they had. Trying to figure it out. They had this theory, and this is what it looks like, right? And it didn't make sense. And there are a couple of theories that kind of explain this part of it, okay, like this one. And then there was another one. I forget who it was. Veen, I think, who had one that explained the high end, but not this end. So they They couldn't figure the whole thing out until Planck came out with his constant, his Planck's constant, and his equation. And look at that thing. That's a hairy equation. I showed it briefly on that last stream, and I said, I don't understand this. And I just moved on. But my brain must have said, hey, you should understand that, or whatever. My unconscious mind must have been working on it, and it came up with it. I remembered it, the equation differently. My unconscious brain did, and it came up with a different idea of why that worked. But it's generally the idea is that you've got there are two parts of this. You got this part here, and I don't know how this equation was derived. You know, I don't know the background behind it. I don't understand. Some of it comes from other work that was done previously. There's a thing called a Boltzmann constant, which relates to the thermal energy of particles and stuff. So, you know, there's a lot more to it. But just 30,000 foot level, there are two parts of this thing, and this part here is the Planck's constant, which is a really small number, and this thing called nu, it looks like a V. I think I called it a V. It's nu. It's Greek letter nu. It's not a V. It's a Greek letter nu, and it represents the frequency. Wavelength is lambda. Looks like an upside down Y. This is nu. Looks like a V, and that's the frequency that you're referring to, that you're thinking of. So if you want to, so if you look at this graph here. Oops, not that one. This one. So if you take, say 4,000 K. So you'd have 4,000 K in here under T, where the T is. And you get this Boltzmann constant and a bunch of other stuff. And so, given the temperature and a wavelength, so you get a temperature 4,000 K and a wavelength, say 1,000 nanometers, and you go up to there and say that point right there, you're going to have this much energy, spectral radiance. This is energy. So you do that for each point here. So at each wavelength, for this temperature, you plug it into that equation, and you end up getting a curve. See, that's how the thing works. But there are two components here. So this component right here has a really big number. Oh, well, they got two different versions of this. Let's use this one. It's a little bit simpler. Okay. So you got the speed of light squared, which is a big number. You got the frequency, which in most cases is going to be a big number, cubed, which is a really big number. But then you got the Planck constant, which is a really small number, n times 2. So as the frequency goes up, this part of the equation is going to get bigger, because this is a constant. That's a constant, Planck's constant. So as this goes up, and it's going to go up exponentially, cubed of the frequency, it's going to go up. So it will go. Normally, it would look like this. It would look like this real steep thing. It would go like that, go straight up. Even more than that, maybe, huh? But then you got this part of the equation, which is 1 over something. So whenever you got 1 over something, as this gets bigger, the number gets smaller, right? Because it's 1 over something. 1 over 10 is bigger than 1 over 100, right? So as this number gets bigger and bigger, this part of the equation gets smaller and smaller. And everything in here, the temperature is what we plugged in, that's set, right? That's what we're trying to figure out at a particular temperature. You got this constant here, Boltzmann constant. You get the frequency, which we're doing for each frequency we're trying to figure out. That's not going to, that's going to increase. And this constant. So out of all these things, this is going to increase. So this whole thing, and this is exponential also. So this is going to increase exponentially. But it's designed so, or it's the curve will. So it's gonna get. This is going to increase, but it's under 1, so it's going to decrease. So as the frequency goes up, it's going to go down. Okay, real rapidly. And when you multiply these two together, you get something going smaller, and this one's going bigger. They kind of cancel each other out at a certain point, and this one is weighted so that it happens at higher frequencies. So you get this one right here, and then you get another, that second part of the equation that goes down like that, and you put them together and it goes up and down. So that's my brain was working on that, and without me realizing, and I woke up and I said, oh, that's it. And, you ever have those aha things where your brain's working on something and you wake up and you have a solution to something or whatever. And I wasn't even, it's not something I assigned to my subconscious. I can assign things to my subconscious, which is kind of weird. I don't know if other people can do that or not, but if I have a problem that's too much for my conscious mind to figure out, I'll assign it to my subconscious, and overnight or over a few days, sometimes it'll come up with the answer for me. And this one I didn't assign to it, but it assigned it itself. My subconscious started working on it and came up with that and said, oh, okay, that's why that does that. So I wanted to explain that. I don't totally understand. I don't know, I don't know the details of Boltzmann constant, and I have no idea how Planck derived this equation. I suspect that learning that would really get into the weeds and wouldn't make good content. This is probably not good content already because we're talking about equations and stuff. People kind of glaze over when you do that. But I wanted to try to make it a little more accessible, I mean, when I first saw it, I didn't understand it, but now it kind of makes a little bit more sense how they're able to get that curve out of that equation. So yeah, I wanted to explain how that worked. At least my understanding now how that worked. Yeah, blue light. Yeah, how to what else did I have in here? Yeah, I didn't have that much, but I wanted to do this experiment too, so and that thing, yeah, how to get that's actually kind of a cool thing. It'd be nice if you could go slower with that though. And it would also be nice if you could show the the full spectrum. I wonder if they have that here. Let's see if they have one in here like that. Visible spectrum. Can we search by GIF here? File type, there we go, GIF. Alright, oh, look at these. Oh, here we go, maybe one of these here. This one's a lot slower too. Looks like we got two different versions of it. Oh shit, sorry about that. That shouldn't have come up. Let's see here. Alright. Visible spectrum. Alright, let me do, I know what to do. Let me find this one and bring it up, and then I'll bring it up. Because evidently that brings up some stuff that we don't want to put on here. CIE luminance. I don't know what that is. This one shows it a little bit. It's slower. This is a particular some particular material that they heat up. But you can see the whole. And this is a little bit more than the visible spectrum. The visible spectrum would be from right here, 700 to 400, right in there. So, yeah, just when it gets really high, this narrow visible spectrum here just keeps going up and up and up. So you can see, and they're showing the color here. This is a particular material that they're heating up, I think. But it still doesn't show the whole, the entire spectrum, like all the way from radio all the way up into whatever UV or ultraviolet or X-ray or something. Okay, well, I can't find one that I'm looking for. So, but anyway, I just wanted to explain that a little bit more. You know, we were talking about that, and there were some unanswered questions, so I wanted to answer those. And okay, now we can do the experiment, I guess, right? So what I have done here is I've set up. Remember last time we did an experiment? I took this. I have this. This here. This is a little. It's a transformer for a train track. It's got little connections in the back, and it's AC, and it's for a little, like a toy trade track transformer. Goes from about 2, when you have it all the way down, it's about 2 volts. You turn it all the way up, it goes up to about 18 volts, something like that. And it's AC. And what we did last time is I just stuck a copper wire in there and turned it up. And as soon as I got up to about 5 volts, it just fried the wire. You know, it glowed really quick and fried within a fraction of a second. And it was a pretty cool experiment. It was fun to watch and everything like that. You know, it made smoke, bright. You know, it lit up, it illuminated, which is what we wanted to show. We wanted to show incandescence and illumination. And you could see, you know, it lit up the whole area here when it fried. So that was kind of cool. But what I wanted to do was to see if I could show the thing glowing in infrared before it was visible in the visible spectrum. So, and I couldn't do that the way it was set up. You know, the calibration or the adjustment here was not fine enough for me to get to, you know, just the right voltage and then current, therefore, because it was a fixed resistance. So anyway, I decided to do a little bit different, and I thought, okay, maybe I can find some material that would have a little more resistance, and then I could, you know, do it that way, just like the filament of a light bulb, you know. And I thought, oh well, I can actually use a filament of a light bulb, and I could break the glass and get the filament and all that kind of stuff. Now that's not going to work because I'll end up burning it up anyway, because it's and then I would have to get it to light up, because it's designed for 120 volts. I'd have to find another transformer, and it would just be, you know, it was more difficult for me. So then I dug around and I found this here. This is a light bulb out of a car headlight. I think it is. I think it's a headlight. And it's incandescent. It's the old-fashioned incandescent type, and it's 12 volts. And so I found, I don't have the proper connector for this, but I found some small little blade connectors that I could put on there, and just some zip cord, and hooked it up to this transformer. And the transformer has what I did is because the adjustment was too much, I wanted to put in some current limiting in there, so I put this resistor in here. I tried another resistor, and it actually, even though this only puts out 2 amps, it was putting out a lot of current, or a lot of power. And it was in the resistors I had in there were not rated for that power. So this one's rated for 25 watts, 5 ohm. Let me show you. Okay. So I just put that in series with this lamp, and that allows me to turn up because there's a huge voltage drop between that 5 ohms of that resistor compared to the voltage drop across this lamp, which is the fraction of a volt. It gives me more adjustment on here. So I can. So what I've got is so now I have a camera here. This see, little camcorder, old camcorder. This is when was this? This is probably early 90s. I got this, maybe. It's tape, videotape, high 8, they call it, 8mm videotape. It's a Sony, old camcorder, and it does infrared, which is what I wanted. So, what I've done is I've got a TV back here that I hooked up. This is all low res, right? It's old. This is 500 line. It's not very clear, but you should be able to see what it's doing. And I think what I'll do is I'll shut off my key light here, because it'll be easier to see. I think I have everything adjusted here in terms of focus. All right. So, all right, and I've got a little asbestos glove here because it might get hot. So what I'll do is I will take. I don't have a way of. This is using RCA. It's a really old way of doing video, and I don't have the proper interface to plug it directly into a source for OBS. So I'm just putting it on a screen back here. And what I will do is I'll point the webcam. There we go. Sorry about that. So I've got this screen back here. I've got the camera, and I will point my webcam at this. Let's see here, and try to adjust it so it gets that that monitor really good. And let's see how I can do that here. All right, I'll zoom in on it. There we go. Okay. And I'll adjust the focus so those letters are in focus. All right, that's pretty good, I guess. And then this light here. So now you should be able to see. There it is. There's the light bulb, right? So there's a light bulb. You can see the little filament on there, I think. Can you see that? There's a filament in this light bulb. And what I'll do is I'll crank up this the voltage on this transformer here just until we detect a glow in that filament. There we go. Okay. Back it off a little bit. You see how there's a little bit of a glow there on that filament? Here, let me turn it up so you can see what's going on there. See? That's really bright. But I'll back it down a little bit. And basically what we're doing is we're just sending, more current through it, which heats it up. Because there's a little bit of a resistance in that. And so what we want to do is heat it up until it's just detectable by this infrared camera here. See, it says night shot there. That's just the feature they had for that. But you can just barely see that it's just barely visible there. Little glowing thing there. Now when I look at this, I don't see anything. I can't detect this with the human eye, but this camera can detect it. So it's infrared, and I'll put it up here in front of my webcam and then try to focus in on it, and there, see, it's not glowing at all. You can't see it even with this webcam, but when I put it on this camera, you can see it's glowing a little bit. So now I'll pump it up just a little bit more. So what we're doing is we're putting more current through it, which is going to make it a little bit hotter. Remember, this is the whole thing with black body radiation. The hotter it gets, the higher the frequency, or the shorter the wavelength. So now it's still not in the visible section, but visible spectrum. But you see it's a lot brighter on this camera. I can't see it with my eye, but I think this webcam actually might be able to pick it up. No, it's still not. Yeah, look at that. Wow. So even the webcam still can't get it. Alright, let me crank it up a little bit more. I'm going to shut this off because I'm getting too much spurious light here. Oh yeah, you can see that it's... So I'll turn it down again, you can see what it's doing. Alright, we'll turn it back up. Okay, so that's going pretty good. I still can't see it with my eye, but I think this camera might be able to see it. So what we're doing is we're looking at... There it is. So this camera can see it now. See that? Just a little bit. But I can see it now. Yeah, I can see that now. So this camera's pretty much visible range. This webcam. So now I can see it. But if I turn it down just a little bit until we can't see it here in this one. I can do that. Okay, there we go. Right? That's below what we can see, right? Pretty much. Below what that camera can see. Oh, there's a little bit there maybe. So it's just barely detectable with this camera. And I can't see anything in there. I can't see it at all. Let me look at it with my eye loop and see if I can see anything. No. It's not in the visible range. It's not in the visible range, but this camera can almost pick it up. You can see it. But then if we look at it with this one, it's really bright, see? So that's infrared. So it's heated up now until it's in the infrared range. But it's not in the visible range at all. And the thing is that as we increase the temperature, the infrared is still there because it's got the whole spectrum, right? It's got that slope to it. So as we pump it up, this gets really bright, and that's looking at infrared because that's what this camera's seeing. But this camera here now is seeing orange almost, right? Let's see here. There we go. So it's starting to go up even more. Now this camera here is only going to see, it's not going to show anything in color because it's not, it's infrared. It's just showing whether there's infrared there or not. It's kind of like black and white or whatever for infrared. But this one here will show actual colors. So if so let me back it down again, back down into infrared here. Okay, so that's infrared. You can't really see it. I'm sorry it's a little shaky. I'm just kind of holding this with my hand in front of the camera. And I'll crank it up a little bit. So now you see it's red, right? It's pretty much red there. But if I give it a little bit more, it should go orange. See, it's getting more orange. And even more, then it starts turning yellow. See that? There's the yellow part in the middle. And you see, and you notice how it's in the middle is where the heat is, right? A long wire, it's going to try to conduct heat away, and so the little leads that connect this coily wire are going to conduct away heat. So the ends of the thing are going to be cooler than the center. So the center is going to be the hottest part of this coil. So the center there, so we've got infrared on the ends, we've got red, and then in the center we've got yellow, which is a higher frequency. So I'll crank it up a little bit more, and that yellow turns to white. And I keep turning it up, and it just then the whole thing becomes white as I turn it up. Now to me, it still looks kind of red to my eyes, but if I keep turning it up, it'll go, white. So now it's it's pretty much orangish, yellowish white now. And you keep cranking it up and cranking it up, and so that's a little bit more fine-tuned of an experiment, I guess you'd say. Let me adjust my camera here again. All right, so that's a little bit more fine-tuned of an experiment, I guess, because it isn't just frying a piece of metal like we did last time. Let me turn this up again so we can see it. Turn it slowly. So, red. Even more and more and more. Okay, so that's the max of this transformer, but it's going through this resistor here. So So that's kind of cool. That's how that's how it's supposed to work. That's how black body radiation works. And I want to check this resistor here just to see what kind of temperatures this resistor is dissipating. Look at that. So there's 200 degrees. This little resistor here on this. It's a power resistor, so it's designed to do that. It's designed to dissipate heat. But I'm probably overloading it a little bit there. It's designed to dissipate heat, but it's also designed to be attached to a heat sink, so you can get the full heat, power dissipation out of it. All right, so that was my experiment for today. The other experiment that we did was I tried to pass my finger through my hand. You gotta watch the VOD. When you watch the VOD, I explain the whole thing, why that was an experiment. I guess I can explain it because a lot of people are watching this maybe who didn't see the other one, and you don't want to look it up. I was trying to explain how, there are no particles. There's no such thing as a particle. Everything is a wave. And the reason why you can't push your finger through your hand is because everything is, when you look at, even if you thought that the electron was a particle, it's a point particle. It has no real radius. They give it a radius for calculation purposes and stuff like that, but it's considered a point particle. But it's a wave. It's a standing wave. Protons are composed of quarks that are waves. Everything's waves, not particles. But the reason why you can't, and when you look at the model, even the old classical model, it's space, and then you have these small particles, which are waves, right? I'll use the term particle, but you understand, there is no such thing as a particle. It's a wave. So you have these particles that are tiny, 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 and then there's a bunch of space. So like the nucleus, and then the electrons are way out somewhere in comparison to the size. Kind of like our solar system. That's not what it really is, but it's all space, right? So you think, why can't you push through if it's all space? And the reason you can't is because of the electromagnetic force, which is what we're all talking about here, is the electromagnetic fields and electromagnetic waves, traveling waves, which is what this black body thing is all about, is transmitting waves. And so you would think that with all that space you'd be able to push matter through each other, but you can't, because atoms on the outside have this electron cloud, of electrons, and like charges repel each other. So the electrons on the outer part of the atoms in my finger and the electrons in the outer part of the atoms in my hand push against each other, and that's why you can't push through things, even though it's mostly space. But if you look at like galaxies in when they watch the merger of galaxies, they go right through each other, because, well, for one, gravity is not polar like the electromagnetic force, right? Gravity is always attractive, but even so, they don't bump into. They just pass right through each other as they merge. They don't bump into each other. The stars don't hit each other because there's so much space. But if the stars were like electrons, the electric force is many, 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 many magnitudes stronger than gravity. So if it acted like gravity, or if gravity acted like electrons, it would be, galaxies wouldn't be able to merge with each other, right? They'd come together, and the force would be so strong that they would just wouldn't be able to push the two galaxies together. If that makes any sense. I'm going to shut that off because it's kind of distracting. In fact, let me get this out of the way too. Hang on just a second here. Give myself a little more breathing room here. I had all these contraptions set up here. So, so we learned about the electromagnetic force. We learned about black body radiation and all that. And I wanted to do this experiment because this was just a better demonstration of what I was trying to get at, or not better. The other one was kind of exciting too. We got to see basically what we were doing is we were repeating that experiment by Ebenezer Kennerly, I think his name was. Let me see. I'm going to try to find here a little write-up about that experiment that I found. It's a page out of a book, but it's Google let me see it, so I guess it's okay. Let's see if I think I got it here under downloads. No. Oh, you know what? I think it's on my other computer. Anyway, it explained a little bit more detail on this guy's experiments that he did. Let me see if I can find that guy's page again. What the heck was that guy's name? Oh, I know how I can find it. All right, we'll go to light bulb. Oh, there it is. Okay. Yeah, let me transition this here. Okay, so in 1761. This is the experiment that I kind of halfway tried to duplicate in the last stream. This guy, Ebenezer Kennerly, he demonstrated that you could heat up a wire using electricity, and he heated it up until it glowed. And he also did an experiment where he took a wire and put a weight on it, and then ran electricity through the wire, and it heated up the wire, and the weight caused the wire to stretch a little bit because it got hot. And then he completed the experiment. He measured it before and after and saw that it stretched the wire. And he thought he might be able to use that for a drawing wire, the way they make wire. And the other thing that I said was not correct. I guessed that they were using chemical cells to produce the electricity, but it wasn't. This was back in the 1700s. This was before, what is it called? The Volta pile or whatever it is. Volta, who made this, the chemical batteries. This was way before that. They were using these Leyden jars. It's basically static electricity. Static electricity was known for years and years, for all the way back. But this guy, after a while, they said, okay, we can make up a little contraption we can turn a crank and it'll spin and it'll rub, wool or amber or whatever they were using to make static electricity, rather than just rubbing it, they would make a little contraction that could spin and produce the static electricity. And then they basically made capacitors, Leyden jars, which were, they made them out of jars because at that time they didn't know what electricity was. They had no idea. This is a new thing. What the heck? They knew about static and getting shocked and stuff like that. But when they after the Renaissance and we started doing real science rather than spirits were doing it or whatever. that they started trying to figure this out, and they thought, okay, well maybe electricity is like a fluid or something, like water or something that they couldn't see or whatever. They weren't sure what it was, and so they thought they could capture it in a jar, and that's where the idea of the Leyden jar came from. Let's see if I've got that. Here, all right, let me do this here. All right, go to this guy. I'll try to find this. Okay, how do you spell that? There it is. All right. All right, so this is a Leyden jar. So they thought electricity was like a fluid or something like that they could catch, or they weren't really sure what it was. And eventually they figured out that they could take a metal rod like this, and they put a ball on the end of it. They didn't know why, but when you make this round like this, it keeps the electricity from draining off. When you have points, electricity kind of dissipates into the air. But when it's round, it doesn't do that. Anyway, they put foil on the inside of the jar, and they filled it with water. For some reason, maybe they thought they could store it in water, like it was I don't know. So and the first Leyden jars they put the foil on the inside, and then they had little machines that could make static electricity, and then they'd put this metal part by the machines that made the static electricity, and the charge would go inside this metal here, and this chain here would touch this foil on the inside, and then while they were holding it, see this guy's holding it with his hand, his hand would actually be the other side of the capacitor. So they had the inside of the capacitor where the charge was going in, and then their hand was the other side of the capacitor. And then when they went to touch it, as they're holding this jar, when they went to touch the metal, they'd get shocked. They basically were making a capacitor. Eventually, they figured out that the hand was part of the formula there, and then they put metal foil on the outside and made it into more like a capacitor. And then they did it without the water. They took the water out because they figured out, okay, that doesn't do any, it doesn't help. And so, that's how they did it. It's basically a capacitor. So this is the thing that this guy, this Ebenezer Kinnersley, was using to get wire glowing to incandescence. It's amazing how they could do that. And I guess he hooked them up in parallel to get the current that he needed. The voltage was really, static electricity. Those Leyden jars, they charge up to 20,000, 30, 40,000, whatever volts. But you couldn't get much current out of them because they didn't have that much actual charge, but if you put them parallel, then you get more current. I think that's what he did. And there was I know what it was. This I'm trying to find this one. There was a write-up that explained how he did those experiments. I guess I gave you the gist of it. Yeah, it's just amazing what they were able to do, you know. And you think about, here's this new thing. They called it fire, something fire. The sparks and electricity and all that kind of stuff. At that time, they called it fire, something new fire or something. I forget what they called it. Eventually, the term electricity came from amber, because amber is something that has a natural charge, with a plus or minus. I forget which it is. And that's what they like to use to make the sparks and static electricity and all that back then. So they called it electricity. Apparently, the Latin word for amber is electric or elect or something like that. And they when they put these Leyden jars together, they put them in series to get really, really big sparks, right, with a higher voltage. And Benjamin Franklin, was in there, right? This is 1760s, right? That's his time when he was doing the kite and the lightning and the whole thing. So he was the first one to use the word battery, because it's like a battery of these Leyden jars. And anyway, so he was the first one to actually use the word battery, but then later on they used the word for chemical battery, chemical pile they call it, or something, pile. Yeah, they used the word pile for a long time. But anyway, so last time I thought this guy was using chemical batteries, but he wasn't. He was using Leyden jars, which makes what he did even more amazing. It's really something else. I'm here. I just plug this into the wall. It's so convenient. I got this little transformer that somebody made for me already, and this light that somebody made for me. It's we forget sometimes how much we rely on all this technology and all the stuff that people did before, and how difficult it was to do things. But anyway, so that's that whole thing. I just thought that was just a interesting experiment, and we kind of halfway duplicated it here. We did it the easy way, but we kind of halfway duplicated what he did. And they eventually they invented the light bulb, right? That's and you could see when I did this experiment last time, you could see it lit everything up. It lit up the whole, just like this light did. I mean, when I fried that copper wire, everything glowed here for a second. My everything, the whole room lit up when it went. And so when they saw that, when they saw that running electricity through a wire like that, I don't know if this guy recognized it, but somebody eventually said, "Hey, that we could use that instead of these, candles and and oil lamps and because that's all they had." They said that might work a lot better, and that was the whole drive behind trying to get a light bulb. It took them 100 years, over 100 years, from the time that Ebenezer did his little experiment to the time that everybody kept experimenting with it, and they kept improving it. They changed materials, the filaments. They realized that it was burning because the atmosphere was causing it to burn, so they put it in a vacuum vacuum bulb. But they couldn't get a real good vacuum, so it still burned. And then what Edison did, Edison didn't invent the light bulb. They had light bulbs long before Edison got in there. Here's one. Look at it. In 1838, This guy invented an incandescent light bulb with a vacuum atmosphere using a carbon filament. That's basically right. That's what Edison did. This guy did it in 1838. Okay, so Edison did not invent the light bulb. What he did is he hired a guy who had expertise in these filaments, who we talked about before. I don't know if he's in this article. Thomas Edison. Yeah, Louis Latimer. He hired this guy who knew all about filaments and how to make them and how they worked and all that kind of stuff. And then he made a bulb. He was able to get a bulb, a vacuum inside of a bulb that was much higher than other people had done by using a vacuum pump that somebody else invented. So Edison really, he was more of a, taking all these little technologies that everybody else had developed and he put it together, and he knew how to make a business out of it. That was his thing. And then also, there was, you had the light bulb, but then you had to get the electricity. Where do you get the electricity from? They didn't have mains back then. They didn't have, there wasn't. So that was another thing that Edison did, right? He set it up so that, they'd have a generator and hooked up to a paddle wheel or something in a river nearby or whatever, and generate electricity that way and run the wires so they could run it through the whole city and light it up. And that's what Edison did. He didn't invent that much, really. Maybe he invented the phonograph, I don't know, or helped perfect it. But yeah, definitely didn't invent the light bulb. Look at that thing. It's funny that we have, you go to buy a lamp. Oh, let me get some here. I want to show you this. This is really funny. All right, I'll be back. 5 seconds. Maybe 10. Okay, so so they got this thing here, and it's designed this way, and even they, this one here is just straight wire, I think, carbon filament lamps, yeah. Darkening a bulb. Oh yeah, it would. That was another problem with this. As these filaments burned off, the smoke or whatever they created would deposit on the inside of the label and make it darker. But so you go, and you go to this. Right? This isn't this here. Let me show you this. If I can zoom in on this and get it focused or whatever. See that? This is a bulb I bought within the last year, I think. And it kind of looks like that, right? But these are LEDs. These are LED strips on this light bulb. And so they put it in a clear bulb. I don't know if I don't think there's a vacuum in there. They got to have a gas in there to dissipate the heat that the LEDs make. So there's some sort of gas in there, maybe an inert gas or just air. I don't know. But it's funny that they made it look like the old-fashioned light bulb. It just cracks me up that they do that, But it has come quite a quite a ways, you know, and you know the efficiency. You know, those light bulbs, incandescent bulbs, the best they got was 5% or something efficiency. So 95% of it. Remember that slope, right? Only 5% of that slope is in the visible range, and the rest of it is all tailed off into heat mostly, and radio, microwave radio. You know, the whole thing as far as it would go. But only 5% of that would come out as light, and so it would heat up. You know incandescent bulbs, right? They heat up. So these are much more efficient. I don't know what the efficiency is on these things now. What the percentage-wise, but it's really good. I mean, you can most of these you can just about handle even when they're on. You can touch them without any problem. Some of them get hot, but a lot of them are so efficient that you can just handle them when they're hot. So that's pretty cool. So what else did I have to say today? I'm trying to think. Oh, damn! I wasn't paying attention to chat. I didn't know I had anybody out here. Let's see. Pywax. Hi, Pywax. I got a chatter here. How are you doing? This was oh geez, he did this a long time ago. I'm sorry I missed your chat here, guy. How are you doing? What are you talking about? Okay, yeah, I'm explaining a lot of stuff. Okay, I guess he went away because I didn't answer him. I didn't know anybody was out there watching or we were chatting. So what else we got here? Equation: object can glow like blue light. Blue light. I think that was it. I think there was something else that I said that wasn't right. But yeah, most of the time, if I say something, I'll preface it. Say I'm pretty sure, or I think this might be the case, or whatever. So it's not like I make a whole bunch of incorrect statements, unless I totally misunderstand it, which happens too, What else did we have? There's something else I was going to look up. I don't remember what it was, but yeah. So that was we did that experiment again. Showed you how black body radiation works. How a conductor can be heated to infrared, but not visible, but it's still emitting electromagnetic radiation. That's what it is, right? Heat, and the electromagnetic radiation was able, for that camera was able to see it. So, and everything, as I said before, everything is, even when this light bulb is off, it's emitting electromagnetic radiation just from the heat. It's above absolute zero, so it's emitting electromagnetic radiation because all the little, everything around here, the atoms are vibrating. Atoms and molecules are vibrating. And that means that the charge carriers, like an electron or a proton inside those molecules and atoms that are vibrating, are moving, and they're changing their vectors, and it's creating electromagnetic waves. That's what black body radiation is. So I think we got that figured out. So I'll figure out something next time we do a science stream. I'll try to we'll have a new subject altogether. It's okay. I don't have enough people to raid anybody with, so I guess we'll just go ahead and and finish this. I've been on for almost an hour and a half. So, all right, let's trying to think if there's anything else. So yeah, give me a follow if you're watching this on the VOD. I don't know if I don't know if they're gonna. Yeah, I don't know if you're watching this on the VOD and you like science stuff. This stream was kind of choppy a little bit. I do a little bit better. You look at my one on the last one I did with the experiments. It was a little bit better. But if you like science stuff, you like technology, I'm going to get better at this as we go along. I'm trying to get affiliate. I don't have affiliate yet, so I need to get more followers to get affiliate. So hit the follow button if you can. I also do, I'm a vegan, been a vegan for a long time, so I can answer questions about that. Tonight I made some vegan ice cream, just without a recipe or anything. So it's just, if you want to know how to make vegan ice cream, I can tell you that. I can, there's a lot of stuff that I know about that. And animals, got a ton of animals around here. I live in rural New Hampshire on a donkey farm, so there are donkeys and sheep and then wild animals, crows and foxes and bears and all kinds of different animals here. I do IRL occasionally. I'm experimenting with that because I didn't want to just sit all the time, sit and stream all the time. So I'm trying to do a little bit of IRL. I can't do real-time IRL because here in New Hampshire they don't have a lot of cell coverage. So I can't use my phone to stream. I can't even use my phone in my house. We don't have cell coverage here. So my IRLs have to be virtual IRLs. I got to take this little GoPro camera here and just walk around carrying my GoPro camera and take pictures, and then when I get back home, then do a stream and play them back and talk about them. So I've done that a couple of times. So yeah, a lot of different stuff. Mostly science and technology. Oh, and then movie. Yeah, we did a few movies so far. I like to do that at least once a week. Have a movie night. The challenge there, of course, is finding public domain movies, especially sci-fis. And we did a review of a movie. We did a review of iRobot. That's in the VOD. You can look that one up. So if you like even contemporary sci-fi, we did a breakdown on that. At some point I want to do Cloud Atlas. I like that movie, and it's very challenging to watch. A lot of people don't get it when they watch it. It takes a few times to watch it to understand it. So maybe I'll do an explainer on that, what that film is about. So yeah, if you're out there watching this, at some point I'll do that. So you might want to watch that movie. It's hard to understand, but it's still entertaining, even if you don't even understand the plot or what's going on. It's got a lot of action and the Hollywoody stuff. So it's still entertaining or whatever, even if you don't totally understand what's going on in the plot. But I'll do an explainer on that at some point. So yeah, a lot of stuff. So hit the follow button, and then you'll be get notices. When I get in the air. I think that's it. I'll probably think of something after I end stream. I'm sure I'll think of something else. But okay, so I guess we're done here. So thanks for joining, and everybody take care. Wear your mask. Wear your N95 mask when you go out. We're still in a pandemic, everybody. So take care. Bye-bye.
Here we go. First thing we climb a tree, and maybe then we talk, or sit silently and listen to our thoughts, illusions of someday, cast in a golden light, no dress rehearsal. This is our life. That's where the hornet stung me, and I had a feverish dream with revenge and doubt. Tonight we smoke them out. You are ahead by a century. You are ahead by a century. You are ahead by a century. Stare in the morning shroud, and then the day began. I tilted your cloud, you tilted my hand. Rain falls in real time, and rain fell through the night. No dress rehearsal, this is our life. Well, that's when the hornet stung me, and I had a serious dream with revenge and doubt. Tonight we smoke them out. You are ahead by a century. 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 You are ahead by a century.